Welcome back. We have just discussed the implementation of GAs to the clustering problem. It comprises two steps. Step 2a, fitness function. We want a function that will take a sequence as the input and produce a number as the output. This number should represent how good the solution is to this clustering problem. The function should quantify how good the fitness of the phenotype is, as defined by the genotype. We can simply use the function we used earlier, where the clustering score is the average intra-cluster distance divided by the average inter-cluster distance. Here, the lower the score, the better fitness it represents. It's important to remember that a better score doesn't necessarily mean a higher score. Our GA will strive to minimize the fitness score, while other GAs strive to maximize their fitness scores. It all depends on the problems at hand and the fitness function. Step 2b, biased selection. Various mathematical formula are used to conduct a biased selection that randomly picks an individual to become a parent, but in a way that is correlated to its fitness score and in comparison to the scores of all the others in the population. This is one example. Here, we first transform each fitness score of each individual in the population so it is 1 divided by the original score. This is a common practice when we want to make small numbers large and large numbers small. Why should we do that? Well, next we will sum all these new scores. As you can see in this illustration, this sum can be seen as comprised of the relative contribution of each individual's score. So an individual that is relatively good and that will have a relatively small fitness score will have a relatively high contribution to the sum when we consider it as 1 divided by the score. All that we need to do now is select a random number between 0 and the sum and take the appropriate individual according to this illustration. For example, look at these 4 sequences. These are the fitness scores. This is what happens when we consider each one as 1 divided by the score. This is the sum, and this is the relative contribution of each individual. Now, every time we choose a random number between 0 and the sum, individuals will be picked in a random manner, but with a bias to the ones with the smaller fitness score. Step 3. Chromosomal crossover. Produce a sequence for the offspring by combining the sequences of its parents. In this step, we will produce an offspring by choosing a random point along the sequence of its 2 parents. Now, we will take this part from parent A and place it along with this part from parent B. Does it always make sense? No. But in some cases, it will combine the best traits from the father with the best ones from the mother. Step 4. Mutation. Add random genetic mutations. To introduce mutation to sequences, we can pick a random letter in the sequence and change it. This mutation in the genotype will produce this change in the phenotype. We will spread a few mutations here and there at a certain rate, with the expectation that some of them will be beneficial and prosper through the evolution process, while others will be harmful and disappear, but only over time. It could also be that a benefit will emerge only when, for example, these 3 mutations appear together, while when each of them appeared in isolation, it was in fact harmful. With enough individuals in the population and enough generations, we can expect a phenomenon of sequences getting worse before they get better, or actually getting worse in order to get better. Step 5. Stopping criteria. In this case, we don't know what is the value of the best possible fitness score, as every clustering problem has an inherent error in it that we just dismiss. So our criterion here is the convergence over time. As you can see in this chart, evolution did take place. And in this case, we see it by the minimization of the fitness score over time. After just 150 generations, there is no additional substantial improvement, so we stop and output the genotype of the best individual. And voila, this is its phenotype. As you can see, it's a pretty good solution. Let's compare it to the results of k-means, which in this case didn't arrive at a good solution, nor to as low fitness score as did the GA. What is the reason for that? The much more rigorous trial and error mechanism of genetic evolution, of natural selection, than the greedy way k-means algorithm uses to find a solution. In this case, we see that the k-means algorithm and the random centroids it began with actually got stuck in a local minimum that they could not get out of. The GA could. In the next segments, we will see a few famous examples of this amazingly powerful technology.